that that's open. I already have this notebook created called direction fields. So the idea is, given some differential equation, we want to plot the direction field for that differential equation. And so kind of see what the topology kind of looks like. So here's a differential equation. It's very simple. dy dx is negative 2x. We're going to have some imports here. We're going to have matplotlib inline, which is a magic command for Jupyter Notebooks. And we're going to import matplotlib.pyplot as PLT. We're going to take in everything from SciPy, integrate, and from SciPy integrate, import ODE, so that we can integrate the ordinary differential equation and plot the slope field or direction field. And we're going to import NumPy as NP for mathematical operations. Cool, so we will execute that box. Now what we're going to do is we're going to create a figure, and we're going to have a subplot with axes, and then we're going to define the vector field for our function. Now, here, that we define the vector field as a function, VF, it takes in a t, it takes in an x, and it's going to return an array where the first element is the derivative with respect to x, and the second element is going to be the actual slope that we're concerned with. So since there is essentially no dx dt or anything like this, we're going to go ahead and set that equal to 1, and then since it's negative 2x, we'll have negative 2 times x of 0, which is the first element in the array, which is x. So that's a little bit confusing, so let's write that out for a second. So we're going to let dy dx so if x is a function of t and y is a function of t, where t is some parameter, then dx dt will be 1. And then that gives us that dy dt equals negative 2x times dx dt. Okay. Cool. So here we have derivative of x is 1, and then the derivative of y is negative 2x. And x0 just references the first element in the x array, which was passed in. Okay, so we want to create the vector field, so we have to create a mesh grid of x and y pairs. So the x coordinates will range from negative 10 to 10 with 20 partitions and 20 elements, and then we're going to do the same thing in the y direction. So we'll have a square grid that's negative 10 to 10, and it will have 20 elements in each position. Okay, and then here we're going to define the u and the v to be just like the vector field from before. And then we normalize this, the square root, divide by the magnitude, and then we're going to do a quiver plot to get the direction field. And then here I just cap the limit on the x-axis, and I plot the x and y axes, label our axes, coordinate axes, put down a grid. Usually I like to do alpha 0.618 for no arbitrary reason. Give it a title, and then we'll show it. So you can see here that the slope is quite positive when it's over here on the left, and then it rounds out and then is quite negative over here on the right. So what this is saying, and we know the solution here, that the solution is going to be y equals negative x squared if you were to integrate this. Okay, so it looks like a negative x squared graph. It's very steep the farther away we are from the axis of symmetry, and then it's quite steep but in the negative sense on the other side of that. And so you could imagine that if these were tangent lines to the function, then it would come up, curl back around, and come back down. Okay, that was an example of the differential equations slope fields and how to plot the slope field in Python. Bye.